This screencast demonstrates the integration of the Air Quality Common Service in the SUDPLAN SMS. The use case on performing an air quality downscaling we want to show here comprises 4 steps. First, we upload an emission database, then we start an air quality downscaling. After that, we want the SMS to visualize the results of this downscaling, which we then finally compare with another downscaling result. Regarding the first 2 steps, the SUDPLAN SMS supports us with wizards. The visualization and comparison of downscalings is done with the help of KISSMap. The Air Quality Common Service allows the user to provide custom emission databases holding local time series. In order to use such emission databases for an air quality downscaling, they have to be uploaded to the SBS before. That's what we want to do now with the help of a wizard. By clicking this button, you start the wizard. As you can see, the first step is to specify the emission grids. We choose the substance of the emission grid and a file holding the grid's time series. Then we choose that this emission grid has a custom time variation and select the appropriate file. By specifying the height of the grid and a name, we can now save the grid. The dialog is split into 2 parts. You already have seen that the right part allows you to specify a grid. In the list on the left, you can see the grids you specified so far, which is only grid 1 by now. Below this list, you find buttons which allow you to add new grids, remove grids, or to save changes. To show these features, we should at least add 1 further grid. So, choose emission grid, a traffic time variation in height, and specify a name. Hitting save, we get a new item in our list of emission grids. By clicking the list items, the view on the right displays the attributes of the corresponding grid. Grid 1, grid 2. By clicking the add button, you can add new grids. Let's do this, constant, grid 3. Removing a grid is as easy as adding it. As we have finished the specification of grids, we can now proceed to the next step. Here we are asked for some metadata of the emission database. The name of the grid, which is restricted to 10 letters or numbers. The spatial reference system, which should be a metric one, and a description. Since this step is pretty easy, we can proceed to step 3. Saving the emission database and optionally uploading it. Since a successful upload changes an emission database in a kind that it isn't editable anymore, we decide to save it. Using the catalog now, we navigate to the new emission database and check if it's valid. Seems pretty good. Perhaps we want to change the description. And save the change. After saving the emission database, we can upload it by using this button and even write the file which is sent to the SPS to our file system. Here we go. Our emission database uploads. And it is uploaded. And the SPS accepted our file, saved it, and we are done. Now we can start an air quality downscaling. An important parameter for the Air Quality Common Service is the geographical grid, which specifies the area for the air quality forecast. As it is such important, we start the air quality downscaling by drawing a rectangle over the desired area using this tool. Then right-click the new rectangle and hit the button Perform Air Quality Downscaling. Please note that it is important that you choose a metric SRS in KISSMAP, otherwise the Perform Air Quality Downscaling action will not be available. As you can see, the wizard which appeared guides you through 5 steps. Additionally, it converted your rectangle into a grid. The first step, Specify Grid, allows you to change this grid. You can move the grid by changing the coordinates of the lower left corner. Or lowering it, putting it to the north and to the east. Of course, you can change the size of the grid as well. This is done by specifying the count of the rows or columns and the size of the grid cells. Your changes will immediately be reflected in KISSMAP. The only thing you can't change is the upper right corner of the grid as it is calculated by the wizard. After we defined a grid, we can now go to the next step, choosing a climate scenario. This step is pretty easy. As you can see, the SMS asks the SPS for available climate scenarios and shows them in a list in the upper part of the wizard. Below this list, you find a description of the selected climate scenario. For this air quality downscaling demonstration, we want to use the ECAM climate scenario and so select it. Hitting next brings us to the third step, specifying the time period for the air quality forecast. This is quite intuitive. We choose a start and an end date, trying to let the start date before the end date. The fourth step is similar to the second step where we chose a climate scenario. This time we choose an emission database. Here we find the emission database we specified earlier. Clicking it shows its description in the right part of the dialog. So let's come to the final step, adding metadata. Here we can enter a name and a description for this air quality downscaling. So we enter something meaningful. And hit the finish button. And here we go. The air quality downscaling is running. The screen is reachable by selecting the corresponding air quality. This screen is reachable by selecting the corresponding air quality downscaling in the tree from the catalog, as well as a screen displaying the input parameters we defined. This button, Show Bounding Box, we can redisplay the geographical grid for this air quality downscaling in KISSMAP. With this grid in KISSMAP, we could start another air quality downscaling. Now we can have some coffee until the air quality downscaling is done. Once an air quality downscaling is done and we downloaded the results, we can go to a screen displaying an overview of these results. By expanding a finished air quality downscaling, we can see its input parameters and the results, like here with Stockholm 2040. Input and results. The result of an air quality downscaling comprises of several time series. Each time series provides information about one specific pollutant or variable for one specific temporal resolution. So if we assume that we have 3 pollutants and 2 temporal resolutions, we have 6 different time series. In order to choose a specific time series, we need to specify a combination of a pollutant and a temporal resolution. The upper part of the appearing screen supports this. The 2 drop-down lists allow you to choose a valid combination of a variable and a resolution. We take PM10 and monthly resolution. After we found a combination we want to see the data for, we can decide what to see with the help of these two buttons. If we want to use the time series for further processing, we can export it to a CSV file. But for now we want to see the time series in Kismap, and so hit Show in Map. The result visualization takes some time, since the time series has to be downloaded and saved somewhere. After the corresponding layers in a WMS are created, we are redirected to Kismap, where the new WMS layer already is added. Which you see here. Just take some time, and it is loaded. By clicking it, a slider appears where we can navigate through time and follow the concentration of the pollutant. This finishes the third step in our use case on performing an air quality downscaling. We have seen how to visualize air quality downscaling results, and now are interested in exploring the results to draw conclusions from it. For this purpose, it's possible to compare the results. To compare air quality downscaling results, we switch to the grid comparison widget, which is reachable via the Windows menu here. The grid comparison widget tells us in the first row that we have to select layers to compare. Since no layer is shown in Kismap, we see it here, or at least no layer visualizing result, we have to add the layers to compare first. I prepared two layers which we will use now. We add both layers, Demo Ecam and Demo Hadley, to Kismap via drag and drop. So we select them from the capabilities widget and dropping it into Kismap. Loading them takes a while. Now we can decide whether to compare Ecam with Hadley or Hadley with Ecam, which we see here. This sounds funny, but as the comparison is based on arithmetic operations, this actually makes sense. As you can see, the next step is to select the style for comparison. We already have defined a European ozone reference style, which maps the colors green to red to the values 0 to 180. But as you can see, the applied color scale produces very similar gradations of green. But the blue shape above the color scale shows the value range of the selected layers. The thickest part of the shape represents the mean value. So we have to define a new color scale. This can be done from the options menu and layer styles. Here we define a name for the new layer style, and then we define the colors. We add a new mapping point, mapping the value 0 to color green, and another one to show red color for the value, let's say 10. Save it, and we got our new demo style. So we apply the new layer style. This causes the layers to be reloaded, which takes some time. The gears in the lower left indicate this loading. As soon as the gears turn to a green tick, the layers are reloaded. Great, the layers are reloaded and we are now able to select the comparison method. But to be able to interpret the results, I will explain the two layers first. So let's hide a layer and have a look at the other one. This layer provides an interesting time series. Let's have a look at the eastern and western part. You see that the western part has a low ozone concentration, while the eastern part has a high ozone concentration. While we navigate through time, we We recognize that both parts switch the concentrations. But what happens with the northern and southern part? Let's go back to January again. Both parts show a low concentration, which pretty soon rises in both parts. After May 2040, we now see that the ozone concentration in the northern part decreases, while the southern part still has a high concentration. But after September 2040, the northern part and southern part switched their roles. So far, this layer. So let's examine what happens with the other layer. This layer is pretty easy. It has a constant time series. The western part constantly has a low concentration, the eastern part has a high concentration, and the northern and southern part show a concentration which is in between. So let's summarize what we have seen. One layer always has constant values. Low concentrations in the west, high concentrations in the east, and something in between in the north and south. The concentrations in the other layer vary. The western part first shows a low concentration, which increases. The eastern part shows a high concentration, which decreases. The northern and southern part have low concentrations, which both rise until May and then diverge. With this information, we are now able to understand what happens when we compare both layers. So we make this visible again, switch to the grid comparison widget, and select a comparison method. Let's choose the average. After the average is calculated, both source layers are hidden and a new object is introduced. This object represents the result. With the help of this slider in the comparison widget, we are able to navigate through time as we know it from the layers. So let's see what the average of both time series is. You see that the result reflects the things happening in the varying time series. But the northern and southern part are a little bit weakened, which is because the constant time series has an average value in these parts. As the eastern and western part are the same for both time series in the beginning, the colors are very bright, and over time, as the concentration of the eastern and western parts switch, the resulting time series shows an average value. Now let's have a look at the difference. The first thing we see is a new color, black, and as we have a look at the color scale, we see its meaning. Generating the difference changes the value range. The visualization now shows a red color for negative and a green color for positive differences. The hints above the color scale tell us what positive and negative differences mean. Comparing the first layer with the second layer, negative results mean that the concentration in the first layer is lower than the concentration in the second layer. If we assume that the first layer provides a forecast for 2030 and the second layer for 2040, this means that the concentrations increase, which is bad. Similar to the negative difference, a positive difference tells us that the concentration in 2030 is higher than the concentration in 2040, which is good. So the colors are just arranged in a way to allow reading the layers from left to right. In our example, red colors mean that the Hadley layer has a higher concentration, and green colors tell us that the Hadley layer has a lower concentrations. If the concentrations are equal, a black color is used. Navigating through time reveals what we already know. The ozone concentration in the western part gets worse, but gets better in the eastern part. And after becoming better, the concentrations in the northern and southern part get worse and then diverge. Last but not least, a second slider was enabled while we chose to generate the difference. It enables us to adjust the color scale on the fly. As we can see in February, the resulting time series has values near 0. This makes it hard to see what happens at that specific point in time, so we use the slider to increase the contrast, which narrows the value range. Increasing the contrast factor to 2 means to halve the value range. This still can be improved. We choose a value range of -2.5 to 2.5 by increasing the contrast factor to 4, and get a result which allows us to really see a difference between the 4 parts. Having shown this, the screencast comes to an end. We saw a complete use case showing the integration of the Air Quality Common Service into the SUDPLAN SMS.